Let's now dive into the details. We will start by explaining how to create repeatable splits of the dataset using BigQuery and how to store them in cloud storage as CSV files. Let's look at two components of the diagram, at the piece of the diagram which will allow us to split the dataset. First, we will use BigQuery to create repeatable splits of the dataset, train, validation, and test splits. Then we will store the CSV files exported from the dataset in cloud storage. These CSV files will then be consumed by the model. And we will also store the trained models in cloud storage. Throughout this module, we use the cover type dataset from the machine learning repository at University of California, Irvine. The goal will be to predict the forest cover type from a number of features, such as the elevation, slope, or soil type. For this exercise, the dataset has been already preprocessed and stored, ready to use in BigQuery. Next, we will see how to run queries from the JupyterLab notebook to split the dataset into train and validation sets, export the results as CSV files, and store them in cloud storage. That's what the dataset looks like. As you see, the target column, which is the cover type, is a categorical variable, so that would be a classification problem. Remember that in machine learning, the best practice is to split the dataset into three sets. A training set used by gradient descent to learn the model parameters, a validation set used to choose the best hyperparameters and best architecture for the model, and finally a test set used to report the performance metric of the final model. Usually, the performance of the model on the training and validation sets is much better than on the test set, because we use these splits during training and tuning. To get a valid sense of model performance, we need to evaluate it on data that has been never seen by the model, the test split. Okay, so how do you craft a query to create a split of the data? For example, if you want to have 80% of your data set in the training set, you can use the rand function within the where clause of the SQL statement. Rand is a SQL function that returns random numbers greater than or equal to 0 and less than or equal to 1 in a uniform fashion. Which means that if we filter the rows with this clause, we'll get roughly 80% of the data, because 80% of the time, that number will be smaller than 0.8. That's right, it's that simple. However, we need a better way of knowing which data belongs to which bucket, that being training, validation, and testing. This will enable us and our colleagues to repeat our experiments. Because the method we just saw won't give you the same result each time you trigger that query, we need a better approach to splitting our dataset in a way that allows us to reproduce exactly the same results. Looking at it even closer, in this example, a simple random function will just grab a new set of 5 randomly selected rows each time you run the query. This also makes it difficult to identify and split the remaining 20% of data for validation and testing. In addition, the dataset might be already sorted, which could add bias into a sample, because adding an order by also creates problems when you use mini-batch gradient descent. As I mentioned, for machine learning, repeatedly sampling the data you have is ideal, so that your experimentation across different architectures and parameter tuning can be consistent. One way to achieve this is to use the last few digits of the hash function on the field that you are using to split your data. A hash function will turn a value like December 10th, 2018 into a hashed numeric value. This hash value will be identical for every other December 10th, 2018 value in the dataset. One hash function available in BigQuery is farm fingerprint. If we hash the date, this approach is now repeatable because the farm fingerprint function will return the same value every time it is invoked on a specific date. You can be sure you get the exact same 80% of data each time. Here's an example of splitting an airline dataset based on the date. If you want to split your data by arrival airport, for example, so that 80% of airports are in the training data set, compute the farm fingerprint on arrival airport instead of date. Looking at the query here, how would you get a new 10% data sample for evaluation? Change the less than 8 in the query above to equals 8. And for testing data, change it to equals 9. This way, you get 10% of samples in evaluation and 10% in testing. We can also take the module of the hash, and because the hash is constant, you get the same hash and the module 10 is the same. So now that is the question of what to hash on. You won't want to hash a data set on the chosen label or on a feature that you use for training, because you might introduce a bias in your training set, and you might also lose some precious information. You need to hash on a field that you absolutely won't use for the classification or regression task, and that's also granular enough for your desired module split. What does granular enough mean? Well, for instance, if you decide to hash on a date field and you choose the year of the date, in that case, you have all the data from one year in your training sets and all the data from a different year in a test set. That might not be good because something might have changed between those 2 years. You want to have data from these 2 years in both your training set and your test set so that you don't introduce a bias by your splitting strategy. You're probably now wondering, how am I going to find a way to balance all these nuances? What if we just concatenate all the fields into a big string? That way, we just need to use the toJSON string function to create a field that's not really meaningful and hash on this new field. That's what we will do in the lab later. Now that we have a strategy for splitting the data, we need to concretely run the query from the notebook. One possibility is to use the bq command. The command shown, bq query, creates the training data split using hash, as we discussed, and store this split into another BigQuery table whose name is specified with the destination table argument. Here, the table is called covertype dataset.training. Now that we have our data as a BigQuery table, we can export that as a CSV file into Google Cloud Storage by using the bqextract command, where we need to specify the BigQuery table that was just created and the path of the cloud storage bucket that you want to export the data to. We use the same process for the validation split, except that we change the name of the table. And an important note, we also change the modules here, so we don't have overlapping splits. So now, let's see how we will write and train the model. Actually, we will both train the model and tune the hyperparameter using AI platform.